Hi, we're going to continue with focus 2. So we'll go on to 2B, where we think about constant pressure situations. So when we did 2A, we talked about delta U. Delta U equals Q if the process is constant volume. But what if it's constant pressure, which is a much more common situation? So when a process takes place at a constant pressure, as a constant pressure situation, if you look on page 46, you realize how things are different. So as energy flows in, for example, to this piston, if the pressure is constant, but the volume is allowed to change because this piston can move, then as heat flows in, energy goes up and the pressure will go up, and you'll see that the piston will move up. So you'll use some of that energy that moved in as heat to do work. So the change in internal energy is always going to be less than Q for these situations. So in order to deal with these situations, we need to define a new function. So we are going to define a function called enthalpy. So enthalpy by definition is the internal energy plus the product of P times V. It's given the symbol H, so enthalpy is H. Internal energy, pressure, and volume are all functions of the state, so they're state functions. Therefore, if enthalpy is defined as a sum of these state functions, it too is a state function, and that's going to be super important for us. So we can talk about infinitesimally small changes in enthalpy, internal energy, and the pressure volume product. So just go from our definition down to thinking about changes, because as we know, it's hard to measure an absolute value for internal energy, therefore for enthalpy, but we'll be able to measure changes. So if P and V are state functions, then we could choose any path we wanted to change pressure and volume. I'm going to choose a path where first I change the volume holding pressure constant, and then I hold volume constant and change the pressure. So that's just one particular path, and if it's a state function, it doesn't matter, so I can pick whatever path I want. Therefore, I can go from this equation to this one, and now I've expanded this to be the sum of those two changes. The internal energy change we can write as a dW and a dQ. We're going to start by making the restriction that we don't have any additional work. So we only have pressure, volume, or expansion work. So it's not so clear. I just want to focus it. So then we can write du as dq plus dw. And we can write work as negative p dv. So we have dq plus now work is negative p dv. But from our second term, we have positive p dv. So those two are going to cancel. And we get dH equals dq plus p dv. And if we carry out a process where the external pressure is constant, then dH equals dq. So at constant pressure, our new defined function enthalpy is equal to the heat transferred at constant pressure. So that's going to be useful for us. So if we measure Q in an isobaric calorimeter, so that's a calorimeter where we hold pressure constant, then we'll be measuring delta H. If we were going to measure Q in a constant volume calorimeter, like a bomb calorimeter, then you'd be measuring delta U. So that would be an isochoric calorimeter. So for solids and liquids, the enthalpy per mole is about the same as the internal energy per mole, because pressure and volume don't change too much. So if you change the pressure, you don't change the volume of a liquid or a solid very much. So this product is very small, and therefore the enthalpy per mole is about the same as the internal energy per mole. So on page 48, there's a self-test where they want you to change or to calculate the difference in, they want you to calculate the difference between delta H and delta U. And I just should make sure that I wrote that right, that they were asking for that versus the opposite, the delta U versus delta H. So yeah, calculate the difference, and they're going to report their answer in delta H minus delta U. So delta H minus delta U is delta PV. So at constant pressure, delta PV equals pressure times the change in volume, because this second term would be 0. So they give us the densities of the tin in the gray form or the white form for the solids. We have a mole of it. So if I have the density and I have the mass of the sample, I'm going to calculate a delta V, it's a V, not a U, in units of liters. So mass of the sample, that's the atomic mass of tin, times the inverse of the density will convert me to cubic centimeters. Then I just convert that to liters, and I subtract the reactant from the product. So I end up with negative 4.41 times 10 to the minus 3 liter difference in their volume, not very big at all. The atmospheric pressure, they say, is constant at 10 bar. So 10 bar times negative 4.41 times 10 to the minus 3 liters gives me negative 4.41 times 10 to the minus 2 liter bars. And if I convert that from liter bars to joules, you can do that with a ratio of the gas constants, or you can remember that it's 100 times difference. You will end up with negative 4.41 joules is equal to the delta H minus the delta U. So they're not very different from each other for solids and liquids. For gases, it's a different story, because we know that pressure has a huge impact on volume. And so if it's U plus PV, if it's a perfect gas, then I can replace PV with nRT. And then if it's isothermal, I can say that delta H equals delta U plus delta nRT. But if T is a constant, then really that second term just depends on the number of moles that change in the process that I'm talking about. So if you have a chemical reaction, for example, where you have 2 moles of gaseous reactant going to 1 mole of gaseous product, then your change in number of moles would be 1 minus 2, so it would be minus 1. So depending on your process, you may or may not have a delta H that's very different than a delta U. If both of these were equal, then they'd be equal to each other. So it just really depends on the stoichiometry or whatever process it is. If it's just a physical change, like if it's a vaporization, or a sublimation, or anything that's taking you from solid liquid to gas or backwards. So how does enthalpy change with temperature? We didn't really focus on this back in Chem 107, but we'll have to realize now that the change in enthalpy for a process depends on the temperature at which it takes place. So we're going to define another heat capacity. So the heat capacity at constant pressure is by definition how enthalpy changes with temperature holding pressure constant. So that'll be a partial derivative. So if we're at constant pressure, we can just rearrange this, take the dt over here. Then we can integrate both sides, and we will find that delta H equals heat capacity at constant pressure times delta T, given the Cp is constant, and that's equal to whatever you would measure as a heat transfer at a constant pressure. So in one of those isobaric calorimeters. So what if the heat capacity isn't constant? Then you'd have to integrate over how it is a function of temperature. So you'd have to say, I need to integrate from T1 to T2, and now I need to integrate how the heat capacity changes with temperature. So not a big deal, but you just have to always make sure that you're checking if the heat capacity is a constant over the temperature range you're at. So how do Cp and Cv compare to each other? So we want to think about it like that first picture we looked at the start of this topic. So if you're adding heat, and you're at constant volume, so this is sealed at constant volume, then all of the heat is changing the temperature. So it's going to take less heat to change the temperature because all of it can be available. If you're at constant pressure, on the other hand, so constant volume, if you're at constant pressure, then this can go up. So as you add heat, your piston can move and you can do work. And if you do work, then some of this heat is used to do that work. So you don't change the temperature as much. So it's always going to take more energy to change the temperature at constant pressure. So it's going to be true that CP should be bigger than CV always. And we'll see in a little bit, for solids and liquids, they're about equal to each other because you add heat and they're not going to expand or compress. So we usually talk, when we talk about liquids and solids, just about a heat capacity. But for perfect gases, we'll see where this comes from in a little bit. For a perfect gas, this will always be bigger than this by n times the gas constant. So number of moles times the gas constant. So we'll understand that better when we get into a discussion of state functions and exact differentials. I think I will stop there and come back and do the rest.